Okay, hi everyone. A lot of the stuff that I'm going to do today is a little bit of review from yesterday and a little bit of new stuff. We're going to talk a lot about limits again today, cover some of the stuff that we did with like simplifying and substituting yesterday, but then also get into like when you can't find limits and when that's not defined. So that's the plan for today. You have a video to watch and then some practice to complete. Okay, so we define limits as a value of a function as the x values approach another value. So this is very weird, but remember that we talked about how like the function is not always defined at the limit. And so if you have like a hole in a function, the limit is still L at C, even if there is that hole right there. So even if the function doesn't exist at that spot, you can still find a limit. So that's kind of the point of a limit. We talked about this one already where we made that table and we found that you could find that the output of this function was 4, even if you knew that it was 0 divided by 0. If you were to substitute this 2 in here, you would get 0 over 0. And so I'm just going to kind of like run through that again where it's like, okay, yeah, I can make a table of values, get close to 2. So like 1.99 over here and then 2.01 all give me values that are very close to 4, even though this is undefined. So we say that the limit as x approaches 2 of this stuff is 4. So we talked about that yesterday. We also talked about these different cases of different functions and how this function looks really similar except for this one spot at C. And so we talked about how if there's a hole but then another spot at which the function is defined, the limit is still L for all of these different types. So this one has a hole here, but it's defined at that function. The limit is L, meaning that the y value of the output right there is L, even though the value of the function is actually not. If the value of the function is L and the function looks like it's approaching that value from both sides, then it goes to that spot, so the limit is L. And last but not least, even if the function is not defined, like I said on the last slide, if there is no definition of what the function is worth at that spot, the limit is still L because on both sides it looks like it's approaching from left and from right. Because I started talking about kind of those two-sided limits, we need to be able to describe and notate the right-sided and the left-sided limits of a function. And so if you have a plus right here, that means you're looking at from the right side. So if you have a function that looks like this, and this is our spot right here, that's C, the right-sided limit is what's happening from the right to the left towards C. This is right-sided. And then the left side limit is what happens when you're looking from the left to go to the right. So the left side limit looks like this, and we're approaching that same spot, but it's different because we're looking from the left. Sometimes you have some weird functions that kind of look like this, where it's like there's a hole or a gap or something, and you can see that the right side limit does not equal the left side limit, and that's kind of an important concept that happens in calculus. So this C value right here does not have the same right side and left side limit, and so when that happens, some weird stuff is going on. We're going to talk about that in a second. Okay, so I have a function. This function f of x is the red function on the graph. We can see that it's defined for x is less than or equal to -4 with this function. So I'm going to put a dot here and I'm going to put an open circle here to represent that it is not the value. So f of 4 is actually 6, not 4, because I have this equal sign right here. Okay, so I'm supposed to look at the left side and right side limits of this function at 2 different spots. So let's do that. We have the right-sided limit of -1 is what's happening from the right side of the graph as we approach the x value -1. And the right-sided limit looks like it's going to 1. The left-sided limit is doing the same thing. It's going to 1 because I can see as you go from the left to the right towards this C value, right, that gives me 1. Since the left and right side limits match, we can say that the limit of the function as x goes to -1 is 1. Because the left and right match. Now, we need to compare that to this other one, which is the left and right-sided limits of at 4, because the left-sided limit, I'll look at that one first. The left-sided limit approaches 6, and the right-sided limit approaches 4. And since those don't match, we have to say that there is not a limit there, or the limit does not exist at 4. Because the two-sided limits don't match. So the left side and the right side don't match, therefore the overall limit does not exist there. That's basically what this first section of this slide says. This portion is for when the two left-sided and right-sided limits don't equal. If they're not the same, then you have to say the limit does not exist. A good example of this is this function right here. This function looks like this, where it's negative for a while and then it's positive for a while. It's not defined at 0, so it opens circles on both sides. And you can see that the left-sided and the right-sided limits do not match here, because this one, the right-sided limit approaches 1 and the left-sided limit approaches -1, and obviously 1 and -1 are not the same, and so we have to say that the limit does not exist there. The other case for when a limit doesn't exist in this class for our purposes is when a function approaches negative or positive infinity at the value. So this graph looks something like this, and there's this asymptote here. And so since there's that asymptotic behavior, the function isn't defined at x equals 0, but not just that, you also can't define the limit there, because you can't say that the limit is infinity. Limits can't be infinity. They have to be a specific value. If it goes to infinity, you can say, like the notation that I used here where I have this arrow is kind of like half okay. If you use an equals sign, it's definitely not okay. So definitely don't use an equals sign. You could use an arrow, but you can also just write it does not exist because it's infinite. I used this slide yesterday, but we didn't get to that third bullet point. The first bullet point is that we have those 3 ways to evaluate limits. We did some practice with that. We're going to do a couple more of that right at the end of the lesson here. We also talked about how the input of the function at a value does not necessarily mean the same thing as the limit. So that's what this sentence right here says. If you put in the C value, sometimes you have that hole, right, where the function is defined in a different place. And the limit here is this spot, but the value of the function is this spot. So that's kind of weird. And then we just really quick talked about the cases of when you have a limit that does not exist. That's if the two-sided limits don't match, or if it goes to positive or negative infinity. I wanted to do 2 examples of algebraic manipulations that will help us solve some limit problems for the day. This is just sort of going towards some more precision, because using the table is kind of okay, using the graph is kind of okay, but really if we can be exact, we should be exact. That's just sort of a mathematical principle. So I'm going to show 2 strategies that will work pretty well. One of the methods, and I can see that I'm going to need something special for this problem, because I see that if I put in 9 here, I'll get 3 minus 3 on the top, which is 0, and then 9 minus 9 on the bottom, which is 0. And so I get a 0 over 0 indeterminate form. And so that means I have to do something else. So Instead of doing that, I'm going to try multiplying by the conjugate of either the top or the bottom. There isn't a really good way for me to tell you that it always should be the top or it always should be the bottom. It's a little bit of trial and error, and I'm sorry for that, but that's just the reality of doing this stuff. So instead of writing this, I'm going to try the numerator, and I'm going to say the limit as x approaches 9 of root x minus 3, but I'm going to also multiply by the conjugate of the numerator. So hold on one second. I'm just going to finish this off. I'm going to multiply by a clever form of 1 that is root x plus 3 over root x plus 3. This whole thing that I just wrote is worth 1, but so it doesn't change the value, but it will really change the way that I write it. So if you FOIL out the top, you get x minus 9, which is good. And then on the bottom, we get something like, what is it? X minus 9 times, I'm just going to keep it, x plus 3. But you know what? I made a little bit of a mistake because there's some specific stuff you have to do when you write limits. You have to make sure you have that limit notation in there, or else it's not really equal. So I'm going to write lim as x goes to 9. Okay, so the limit as x approaches 9 of x minus 9 over x minus 9 times x plus 3. Well, check this out. I have this thing that cancels. This whole thing will cancel. And so I get 1 over, oh, I did it again, limit as x approaches 9 of 1 over x plus 3. And now I'm at the spot where I have done some simplifying, and all of this work allows me to now take this 9 and put it in and see what I get out. Because now I've got 1 over 9 plus 3 is 12, so I've got 1/12. And now I don't have to write the limit anymore because I have evaluated and I've said the value of this limit is 1/12. The next one on the bottom here is just going back through factoring. I know most of you know factoring really well, like in and out, and you should trust your ability at this point. Just make sure you have that limit notation. And you can see that I'm kind of writing this in half cursive, and that is sort of the tradition with limits. You just kind of do it in cursive. I don't really know why. Denominator factors as x minus 4 times x plus 2, no, x minus 2. And then I get that thing that cancels. So let's just cross that off real quick. These cancel, and I'm left with the limit of x as x goes to 4 of, here I am not writing it in cursive after I just made that a big thing, 1 over x minus 2. Put in 4, I get 1 over 4 minus 2 is 2, so I get negative 1/2. Again, I'm going to put a box around it, and I'm not writing the word limit there because I have evaluated the limit, and now I know what the expression is worth. So once you have evaluated, you don't have to write the limit thing, but as you're working through the algebra, you kind of are supposed to. I don't know how picky I am about that, but I know that that's like a thing that people get really aggravated about when people don't write those limits in there, so just be very careful about that. That's all I have for you. So watch out for the times when you need to use algebraic manipulations. If you get stuck doing algebra and you're like, I really can't even see a path forward, that's when you should start thinking about, okay, do I use a table? Do I use a graph? Or is there something else that I'm missing that I can work with a partner to figure out? This should be plenty of information for you to get through the worksheet for today. I will see you all on Thursday, and we'll spend a little bit more time working with limits and talking about some more stuff that we can do with them.